Abdullah, and my team members, Al-Imran and Nguyen. Our faculty supervisor is Dr. Sigar. We'll be discussing the feasibility evaluation of a novel ultrasonic method for prosthetic control. Now, people who have gone under amputations of hand find it difficult to perform the daily tasks we all take for granted. Because current prosthetics are unable to non-invasively utilize the fine motor control, including thumb oppositions. In order to utilize the fingers for prosthetic control, you must use deep muscles that control the thumb and complex muscles that control the forefingers. The problem with existing technology, electromyography, which is also known as EMG, uses surface electrodes to acquire electrical signals for the surface muscles. However, EMG requires needle electrodes to target deep muscles, as you can see in the picture, and this is invasive. Now, our objective is to design and evaluate a system for detecting and quantifying the muscular motion of the forearm with ultrasound. Just to demonstrate what muscles we are looking at, here's a picture of the cross-sectional area of your forearm, and we are viewing the muscle controls your thumb, which is called flexor pollicis longus, located right here, and the muscle controls your forefingers, called flexor digitorum superficialis, which is located right here. And here is the video of our ultrasound taken with our system. What we are visualizing over here is basically changes in echogenicity. It's basically when muscle contracts, you will see a darker spot under ultrasound right here. Now, for the system requirements, for each finger, our system should be able to correlate the muscle contraction with degree of contraction, for instance, full contraction or half contraction. Also, the rate of contraction, meaning how fast you're contracting. Also, portability and cost effectiveness are part of our system requirements. Now, here's the design of our system and how it functions. So, we are using the 7.5 megahertz intercell probe, which is loaned to us by our faculty supervisor. And we have divided our system into 3 stages. First, setup. What we do is to position the ultrasound probe and then get the ultrasound videos and import it in MATLAB. Secondly, we move to the training stage. Over here, we automatically locate our target muscles and then select the finger location. Once the training is done, our system is ready to be used to, during processing, to identify the finger. Once the finger has been identified, then it can estimate the velocity and degree. Now, in order to get reliable results and have a stable platform, we build a cup which provides positive downward pressure against your skin. And also it allows a wide range of angular alignments, and it secures the probe at user positions, user-defined positions and defined angle. And also it gives us the repeatable results. I'm going to pass them to.
So our system, ultrasound matching via template, ultrasound motion assessment via template matching, or US MATM, is able to reliably identify the contractions of the thumb, index finger, and middle finger. It's also able to estimate the rate of contraction and degree of contraction correlating with these contractions. This is all done with a low-cost, very portable probe that enters in 75 megahertz probe. Okay, so when the user is using our system, they're first presented with our GUI interface. The GUI interface allows the user to select the size of the windows, create the windows, and then train the individual thumbs, index finger, middle finger, and ring finger. So in order to train your fingers, the user is instructed to perform complete contractions repeatedly for about 13 seconds, in this case, say the thumb, and our system identifies the area of greatest motion as shown right here. Okay? In order to determine the area of greatest motion, our system overlays a series of overlapping windows. Basically, it subsegments the entire video into smaller areas in which it performs motion assessment. Basically, it determines the total motion within a given area. It performs this via a sum of difference algorithm. The sum of difference works by, in our case, by taking a template while the user's at rest and comparing that template with all subsequent frames. If there's a difference between the template and a subsequent frame, by summing up all the pixels in that frame, you're able to get a single value that is the total motion within that region. So what we're able to do is by training each individual finger, we're able to identify the regions in which the motion is occurring with an ultrasound. For instance, we have the thumb, middle, index, ring finger, and those associated areas estimated by this graph. Notice that there's some overlap in these regions. This is because our system does have a little crosstalk, which I'll talk about a little later. So to show you how sum of difference works, notice the contraction that's occurring here. Whenever the contraction occurs, there's a positive inflection in the waveform. When the user goes back to relaxation, the waveform goes back down towards zero. Okay, so the result is we're able to overlay these windows, and we can automatically identify the difference between the thumb, flexor pollicis longus, or the four fingers, the flexor digitorum superpellis. In this case, we are unable to automatically, but we can with user-guided training, identify between the individual contiguous fingers. The reason for this is the prevalence in crosstalk in this flexor digitorum superpellis. Essentially, this muscle controls the four fingers. In fact, it's so difficult that I challenge anyone in this room to move their middle finger without moving their index or ring fingers. So in order to get increased specificity, we allow our user to utilize a video to help guide our system. This is a sum of difference ultrasound video, basically the difference. And notice right here where the difference is occurring. Our users are instructed to watch this video, identify this, and then place a small box around that area, as small specifically as possible. This gives weight to this region, so our system is able to identify this region as a contraction associated with, in this case, say, the thumb. So what's the total output? Well, we're able to identify the individual finger motions. In this case, I'm going to show you a short video of a user contracting the thumb, followed by the index finger, followed by the middle finger, followed by the ring finger, in rapid succession and repeating. I'm going to place an array of overlapping windows over the regions in the ultrasound where these contractions occur. Our system can identify these contractions in year. So now that we've identified which finger is being contracted, our goal is to extract extra information from these signals. We do so by determining the degree of contraction. The degree of contraction is related to the total inflection of the sum of difference algorithm, or the total amount of change in a given window. In this case, right here, degree of contraction, complete contraction has a large inflection, and partial contraction has a slight one. Rate of change is determined by the slope, which is taken between 20 and 80% of max height. This slope varies based on how quickly the user flexes their finger, fast or slow. And then finally, the duration of contraction is performed by measuring the width of contraction at half height. In order to illustrate the slope, notice the green line here, which represents a relatively slow contraction, and the red line here, which represents a fast contraction. Our results show a 1.9 or a 2 value here for slope on the slow, and a 12 on the fast. That's an order of 6 variance. Okay. Same thing for degree of contraction. A complete contraction will have a higher inflection, total inflection, than a slow contraction. In this case, we show full contraction, moderate contraction, small contraction, slight contraction. If you take a look at the full contraction versus slight contraction, blue and green, you'll notice that we have a 487 versus a 41. That's about an order of 10 difference.
In order to verify the results of our system, we hooked it up to a mechanical system based on rotor encoder with a pulley attached to the top. We then attached the end. We then attached a string to the end of the finger, so as finger flex, we would be able to get the angular position and from that get the get the velocity and the degree of contraction. After hooking up to an IDAC, we read the rotary encoder in LabVIEW, which saved the position as well as the system time in a text file, and we saved that text file and then imported it in MATLAB to process for that. And this is a graph of our system. On the x-axis, we have our measured velocity in millimeters per second, and the y-axis is the sum of pixel intensities, the rate per change per second. Notice you can see a linear correlation, which we were able to do with a non-invasive method for viewing deep and complex muscles. You should also note that the variance may be due to isometric contractions where you're generating tension in the muscle, but the muscle has not yet begun. And using the same two subjects as the previous slide, we also used the displacement to correlate with the degree of contraction. On the x-axis, we have the millimeters displaced as viewed by the rotary encoder versus the sum of pixel intensities. You can see a possible linear correlation, again due to isometric contractions, as well as a recent malfunction or probe that we can definitively say is our system is able to non-invasively view the deep and complex muscles, and that we're able to identify the finger motions from the thumb, index, and middle fingers. And from those fingers, we're able to estimate the rate as well as the degree of contraction. All of this with a relatively low cost, low resolution ultrasound probe. And from our system, we can potentially from there generate a control system using a stepper motor. A stepper motor moves a predefined distance when you send an electron impulse to it. Using multiple motors, we could have a 2-bit selector to select between the motor. And increasing the degree means you send more pulses to that motor, and the faster you send those pulses to the motor, the faster the motor will turn. What we would still like to do with our system, even though we've accomplished a lot, there's still more that we might want to do. We would like to more reliably identify between the index and the ring fingers, and we would like to narrow our estimated range and allow multiple tools to interact as well. Some of the greatest achievements of our project is we've been awarded a provisional patent because this is a novel approach where ultrasound has never been used to control a prosthetic limb. We presented some preliminary findings at the BMAS concert this past October, and we're currently working on publishing a manuscript with the results. From our system that can identify individual finger motions and estimate the degree and velocity of contraction. I would like to give a special thanks to our faculty supervisor, Dr. Sikar, as well as Dr. Pancrazio, and the other faculty, as well as our